Okay, so we are going to measure rate of reaction using different concentrations to determine the rate equation. In the last video, we used a continuous method where you continually monitor the volume of a gas produced. This one, we're going to use an initial rate method, which is generally speaking much more efficient. So you just measure the time taken for the first bit of the reaction to occur, and you can get many more data points and get some good results from it. Okay, so the reaction we're looking at is between potassium iodide and hydrogen peroxide. Oxidation state of iodine is there, it's -1, and it gets oxidized to 0. And the hydrogen peroxide is the oxidizing agent because the oxygen's got an oxidation number of -1, but it gets reduced to -2 there. Potassium and the sulfate ions are spectator ions. Right, so let's see what would happen if you did this reaction. You'd have a beaker and iodine. All of these reagents are all colorless except for iodine, which is orangey color, yellowy orange, yeah, not really orange, that's more that color. Right, that's iodine in solution. So what would happen here is if you added all these reagents together, you'd just notice that it would start going slightly yellower and it'd get darker and darker and darker. Right, now you may think, oh, you could use colorimetry to measure the darkness of the iodine. That's going to be a continuous method though. We want something different to that. So what we actually do is we add a little bit of starch also into, we add some starch, and what that will do is as soon as you make any iodine, it goes black. Okay, so iodine and starch, it goes bluey black color. That wouldn't help as much. As soon as you start the reaction, then it would immediately just go black. And that wouldn't really tell you anything at all. So what we do is we use a second reaction here to destroy the iodine that is formed. Second reaction to remove some of the iodine, okay? And the reaction we have is thiosulphate reacts with iodine. Thiosulfate is reducing agent, it reduces it back to 2I-, and you get S4O6 produced there. Okay, so we're going to use this reaction. So every single reaction vessel, we're going to add a little bit of thiosulfate just to chew up the first bit of iodine that is produced. All right, so in this beaker, we're going to have all of these chemicals. We're going to have the same concentrations of every single one. The only thing we're ever going to change is the concentration of the iodide ion of Ki. So we're going to change that. So we're going to do this experiment multiple times, maybe 6 or 7 times, and just change the concentration of iodine. Okay, so let's think about what's going to go on there. Now, what will happen to the concentration of iodine during that reaction? So here we've got time, and here we've got the amount of iodine produced, or the concentration of iodine. I'll just have the amount of iodine. Right, it's going to go up like that, isn't it? It's going to go up. Okay, and the reaction will slow down towards the end up here because the reagents are running out. And right, we're going to put a bit of thiosulfate in there. We're going to put enough thiosulfate in to destroy this much iodine, little red mark there. So there's enough thio, S2O3 2-, to destroy, to react with, destroy sounds a bit dramatic, to react with the first bit of iodine. Okay, it's here. So if we can imagine what would happen in that graph then, right, do that line across there, do my arrow down, call that time t. Before time t, we wouldn't see any color change. It would just remain clear because any iodine that was being produced would be destroyed. As soon as the thiosulfates run out, then at that point, the reaction will suddenly go, at that time t, the reaction, it will go black. Very quickly. It's quite nice and dramatic, and you have a completely colorless solution, and with the click of the fingers, it just goes black. Okay, so we're going to measure that time t. Let's see what would happen if we used a slightly more let's say more concentrated solution of iodine, of solution of Ki, higher Ki concentration. The reaction would go faster. Okay, we go like that. So this time, the time taken would be there. That green T would be a bit shorter. Let's do a much more dilute one. Let's have the yellow. Right, so this is a much more dilute one. It's a much slower rate of reaction. Let's level out till there. Right there, time t would be there. So now you can see that time t is going to give us an indication of the of the initial rate. What is the initial rate? It's the gradient for that first bit of the line up to time t, isn't it? So hopefully you can see there that the gradient, which is equal to the initial rate, is going to be proportional to 1 over t. Yeah. So the bigger the value of the t is, the less the gradient. You can see that the yellow one it's got the biggest value of t, and that's definitely the least steep line. So that's how the thiosulfate works for us. Then it destroys the first few percent of the reaction of the iodine produced, and at the same amount of thio, so it's the same one for each experiment. Then we can do multiple concentrations of Ki. So we get lots of values of K, concentrations of Ki. So what we've got here is we're going to have conc of Ki, which is really just I minus, yeah. And here we're going to have time to go black in seconds. And then we're going to do a little bit of calculating here. So we're going to do rate, and rate, which is going to be equal to 1 over time. You can do 1,000 over time as well. It tends to give you bigger numbers, so rather than decimals, so we're going to get a series of results like that. We could maybe do 7 different concentrations quite easily. That's just 7 little beakers, and you just time how long it takes to stop. So we can do, like, rather than the other continuous one where you're having to measure the volume of hydrogen for minutes after every time you started it. So we've got our results there. Then we've got all the data we need. We've got the concentration of I minus against rate to see, if we double the iodide concentration, do we double the rate or do we quadruple the rate? So we can tell if it's first, second, or 0 order. But there is a bit of a better way of doing it than that. And what we're going to do is we're going to get these results, and we are going to linearize them. So we're make them fit on a straight line. And why is it a good idea to linearize results? Because then, if you get results like this, if you're trying to draw a straight line of best fit, it's very easy. You just get a ruler. If you're trying to draw a curve of best fit, it's much more difficult. So we can get the line of best fit, and from that we can work out the order of reaction. But let's do this little bit of maths that you need to do that. They wouldn't ask this on the exam, but it's not a bad idea to know it anyway. So if you don't do maths, I just bear with it. Right, so you need to know about logs, which you will do in the pH topic if you haven't done them already, if you haven't done them in maths. But anyway, we've got the equation. We know that rate is equal to a constant times by I, and I'm going to say, let's say that to the power of A, where A is the order with respect to iodide lines. Just note really that this is not really a rate constant, because the full equation would be rate rate constant I minus all the other reactants, H plus and H2O2. So, but why can we say it's a constant? Because what in our experiment, what we've done with it, and we don't know what these, that could be A, we don't know what the orders of these are either, B, C, but what we do know is all of that is constant in our experiment, because the only thing we changed was this, the I minus concentration. So that K there, it isn't the rate constant strictly, but it is a constant. Okay, so if you take logs of both sides of that equation, we'll do log 10. You can do, you get log rate is equal to log K. We're not really interested in K. Now what happens when you take a log of an indice, that comes down in front of it, so that's going to be plus A log I minus log concentration of I minus. So we're now going to make this fit into our log graph of a straight line, which Y is equal to mx plus C. And there's a few occasions in the course where you need to do this, so even if you don't do maths as well, just to get used to it. So on the y-axis, we're going to plot log rate. Okay, that's y. The thing that's changing all the time, x, well, that is the concentration of I minus, that goes there. This intercept is going to be the log of, say, we're not really interested in the intercept. In fact, we're not even going to probably know the intercept, because we're not going to plot the graph, you know, with the all four quadrants, yeah. But what we do know here is, sorry, that is made a mistake there. X is not I minus, it's log I minus we're going to plot. That is the intercept, which we're not really interested in. But that just tells us then what we are interested in is this A is going to be the gradient of the straight line. So here what we do is we plot our graph. And on here we have log of the rate, log base 10 of rate. On this line we have log of the iodide concentration. We won't plot this, that won't be 0 there, because you probably end up with some negative values, your logs and stuff, so don't worry about that. And then you're going to get all your points, so 7 points. You can see that one is obviously anomalous, so we're going to leave that one out. Draw a line of best fit. And then all you've got to do is work out the gradient of that line. And what is the gradient equal to? The gradient is equal to A, which is the order with respect to I minus ions. So when you get A, if you got 1.98, obviously that can only have integer values, it would be 2, and so on. So that is required practical 9B, I think it is. And it wasn't this experiment, but it was a very similar experiment. It came up a couple of years ago. They said there was a second chemical they added to destroy the first few percent of the one that was made. So they didn't say it was thiosulphate and iodine, but that's what it was all about. So it's as well to know that this one well. And as I say, this allows you to get multiple data points quite quickly, unlike the continuous method. And then using this log plot enables you to put them on a straight line and spot anomalies very easily. And it gives you good, accurate results.